Again, first Gallagher lecture of the season of 6 that we plan to have, first one in person in a long time. Again, I am Steve Hubbard, the department head of Geoscience. As I mentioned, we have organized this as a hybrid event. We were pretty pleased with the engagement we had with folks during the pandemic. We've got a pretty full room here, which is amazing, and we've got 100 people online. So seems like a great start to our effort to bring this talk series beyond the building here today. Before I do begin, or we really get going, I want to take this chance to acknowledge the land that we are privileged to live and work on here in Calgary. These are the traditional territories. Locked out, they saw me talking. These are the traditional territories of the people of the Treaty 7 region here in southern Alberta, which includes the Blackfoot Confederacy, and comprising of the Siksika, the Piikani, and the Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bearpaw, and Wesley First Nations. The city of Calgary is also home to Métis Nation of Alberta, Region 3. We also acknowledge we are standing on land that is situated immediately adjacent to the Bow River, a river that has shaped this land and its people for generations. The traditional Blackfoot name of this place is Mohkinstsis, which we now call the city of Calgary. Since 2015, the Department of Geoscience and Faculty of Science has had the privilege of organizing the Gallagher Colloquium series, typically in this room. These presentations have allowed our department and our faculty to welcome and host world-class researchers who all share a passion for science, scientific research, and exploration. I'd like to, before we get going, I'd like to really make sure I take this chance to recognize the Gallagher family for making this series possible. Their generosity and vision for deep connections between the university and the community is so appreciated. Their support allows us to promote and build public awareness through talks like this for science and scientific research. And it helps people understand why science is fundamental and important, not only to our own lives, but to the world we all live in. Particularly important these times, it seems. So we are truly grateful to be able to host this series. So tonight, I have the distinct pleasure of welcoming Dr. Ben Tutolo, an associate professor in the Department of Geoscience here at the University of Calgary. Ben has worked in the department since 2017, so I know many of you have got to know him. If not in this forum, well, you've seen him in this role, introducing speakers and helping to arrange them. So it's really a pleasure to turn the floor over to him for the highlight of the night tonight, I think. Before coming to Alberta, Ben did his undergraduate degree in environmental systems engineering at Penn State University and his PhD in geology at the University of Minnesota. From 2015 to 17, he did a postdoc at Oxford University. And here at Calgary, it makes a big impact teaching various geochemistry-focused undergraduate and graduate level courses. His research, we'll learn quite a bit about here tonight, focuses on the reactive movement of fluids, solutes, and heat in geologic systems. He measures the physical and chemical properties of rocks, water, and gases sampled in the field, and those produced in the laboratory to develop numerical models of these processes. Ben is currently a participating scientist on the Mars Science Laboratory Curiosity rover team, and was recently awarded the 2022 Mineralogical Society of America Award for contributions to the science of mineralogy by a research under the age of 35. Very impressive. It's a real pleasure for me to get this chance. Ben is young, but his trajectory is clearly on the rise, and I don't see it pinnacling anytime soon. So please, I think we can all appreciate where this is coming from. Join me in welcoming Ben, who will talk about.
What am I going to talk about? All right, thank you very much, Steve, and thanks everyone for coming. Thanks to you out there online for tuning in as well. So today I'm going to talk about salty waters, life's origins, and biological habitability on Earth and Mars. As Steve said, I'm part of the Mars Science Laboratory mission team, but today I'm speaking as Ben Tutolo, Associate Professor at the University of Calgary, not as part of the team. I'm not going to say anything outrageous today. How did life begin? Right? This is a fundamental question that's been pondered since the dawn of civilization, right? Since the very first indigenous peoples were thinking about their creation stories, this question has been at the top of mind. There are many people around the world today, very, very smart scientists working on the geochemistry or the biochemistry, sorry, of how life began. What I can do as a geochemist and a geologist is answer a very relevant additional question: where did life begin, right? So Mars and Earth both have had environments over their history where life could have began. And what I'm going to talk about today is constraints that we can place on those systems by studying the surface of Mars and the surface of Earth today. So habitability is this word that gets bandied around in lots of fields in the geosciences, in particular in astrobiology and planetary science. But what does it actually mean? Habitability means somehow you're bringing together the ingredients for life: carbon, hydrogen, nitrogen, oxygen, and phosphorus, or schnapps for short, which hopefully we can all have some later. Energy, light and heat, right? Coming from the sun, coming from geothermal sources. The most important thing that we all think about when we think about life, the solvent, water, right? Follow the water. And lastly, conditions: temperature, pH, salinity, activities of water that are needed, where all of those things overlap in a way to bring them together in one place. We call that habitable. That's a habitable environment. So on the left-hand side, we see Earth, a place we know and love, obviously habitable. If humans have their say, it might not remain that way. Mars, as I'll show today, was once habitable. Today, probably not so much. So there's this really lovely children's book written by Canadian authors and illustrated by Canadian illustrators, when planet Earth was new. And when they talk about the origin of life in that book, they show this, just waves, right? Leave it to your imagination. And I think working on this question of how did life begin, where did life begin, allows us to imagine, right? Use that part of our creativity as geoscientists, as geochemists, to think about how and where life began. In all cases, we know that water must have been there, right? So I really love this illustration because water is the only thing we know for certain that must have been there. So as we move on through tonight, we're going to have these questions. There's 3 of them throughout. So our first question that we're going to ask today, which is very key in stabilizing the water on the early Earth or Mars, is this question: which of the following was not a significant component of the atmosphere of early Earth or Mars? Oxygen, nitrogen, carbon dioxide, or hydrogen? You can go to slido.com. There are QR codes throughout the room where you can answer this question. And once we get enough responses, we will share the response. Everyone guessing the same thing. Seems like everybody is confident there was probably some CO2. Nobody has voted for that one yet. Oxygen is getting a lot of votes still, 90, 80% of the votes. Hydrogen, seems like there's a battle here between hydrogen and oxygen. Nitrogen, I'm not sure. Okay, so the answer is, of course, oxygen, right? Our planet has only had oxygen since the time that photosynthesis evolved, right? About 2.5 billion years ago. Before then, there was no oxygen in the atmosphere. This thing that we need so much to live and be animals and digest our food simply was not present on early Earth or early Mars. Hydrogen was there. And so we'll talk about now the importance of hydrogen for the beginning of Mars. Okay, so Mars used to be warm and wet. Now it is cold and dry, as shown on the right-hand side. This is a very nice paper from Wordsworth and others in 2021 that goes through the history of aqueous, or signatures of aqueous alteration that we see on the Martian surface since about 4.5 billion years ago, since the beginning of the planet. We see things like valley networks, crater degradation, basin lake formation must have had liquid water there. That's aqueous geomorphology. And then on the other side, we see clay minerals, phyllosilicates, sulfates and evaporites, manganese oxides that had to have formed through aqueous-driven alteration. And this is a history of the millions of years that were warm on the surface of Mars over that time scale. What you see, this is a cumulative histogram. As you go through time, the number of millions of years of warm conditions above freezing on the surface of Mars increases, and then around 3.5 billion years ago, no more warmth. And what is driving that warmth and what ultimately made it go away is hydrogen. So there was oxygen, some oxygen in the early history of Mars, not a significant amount. But in the end, hydrogen was the extra kick, or gave Mars the extra kick that it needed in order to stabilize liquid water. Hydrogen can be a very potent greenhouse gas on the surface planets. And so these alternating cycles between the blue and red lines here are thought to be the times whenever you have significant amounts of hydrogen that allow you to stabilize liquid water. So a warm, wet, early Mars apparently needed hydrogen to trap heat. How do planets make hydrogen? A fun reaction known as serpentinization. It's one of the most fundamental reactions that happens on any planet. And it has happened on our planet since time immemorial, since there was water and rocks here. Serpentinization is common. It adds water to this rock here, peridotite, which is full of the mineral olivine, this green stuff, oxidizes that iron and produces hydrogen. So here's mantle peridotite, a nice sample called dunite. To that, we can add this much water, a nice big beaker of water, 1,302 milliliters. Why am I being so specific about that? Because this rock on the right-hand side contains exactly that much water, all tied up in the mineral structures of serpentine and brucite. So in the process of going from olivine-rich mantle peridotite, we add water and we become a serpentinite. In that process, we generate hydrogen. Okay, so I'm going to show a couple of diagrams here, and I think it's important to take a minute to walk through what exactly is being plotted here. So again, we're talking about oxidation of iron. That's the process by which hydrogen is produced. On the y-axis here, I've got the amount of oxidized iron over total iron. And on the x-axis, we've got loss on ignition, which is a proxy for the amount of water in the rock, or water weight percent, which is the actual amount of water in the rock. So you can think of this going left to right as the degree of serpentinization. Rocks on the right-hand side are fully serpentinized. Rocks on the left-hand side are that green, beautiful mantle peridotite. And up on the y-axis here is that process of iron oxidation. Okay, so we start with this nice olivine-rich rock on the left-hand side here. We add water to it. We make beautiful serpentine minerals like plotted in that image up there, and hydrogen gas. And that hydrogen gas is important to warm early Mars. And so we can take that number that was plotted on the y-axis before, so that was the fraction that is oxidized iron. Now, if we just take the weight percent and assume that all of the initial iron was in the reduced form, we can actually calculate the number of moles of hydrogen that is forming per kilogram of rock, which is shown here. And this will become important later when we talk specifically about the role of serpentinization on Mars, because this is the terrestrial example. This is how much is produced from serpentinization of Earth's mantle. Serpentinization on Mars would have done something quite different. Because not olivines are created equal. So Earth's mantle here on the left-hand side, these beautiful green olivines plotted in this dunite. These rocks, this right-hand side here, I'm sure you've seen this in Banff or in any rock and mineral collection around the world. This is a palisite meteorite. That stuff is also olivine, right? But those olivines look very different because they have very different amounts of iron in their structure. So not all serpentinization is going to produce the same amount of hydrogen because the iron oxidation is the most important part. To plot this for you, to really quantify it, we can talk about the olivines of Earth's mantle and compare them to the spectrum that is possible in olivines in general. So here is an olivine from the terrestrial mantle. It's got about 10% iron in it, which means that it's mostly this mineral, forsterite. If we then go to the other end of the spectrum, we have phthalate. That's the iron-rich version of olivine. So olivine is what we call a solid solution. So it's a solution somehow between the mineral phthalate and the mineral forsterite, and the terrestrial mantle is mostly 90% or so the mineral forsterite. Okay. How do Martian olivines compare, right? Does anyone have an intuition for what that's going to be like? It's the red planet. They've got a lot more iron, right? Fortunately, Curiosity has analyzed those olivines in situ on Mars. It has been able to scoop up samples of Mars, put them into an X-ray diffraction instrument inside of its body, and analyze those olivines. This is what that looks like. So here's Curiosity. It scoops up a sample, dumps it right there into its belly, and it has an X-ray diffraction instrument, just like we have upstairs here in the Earth Sciences building, that is able to analyze the mineralogy of those samples. And about 4 of those samples so far have actually still contained the mineral olivine. It hasn't been altered. And what that tells us, what those samples tell us, is that all of that olivine is much more iron rich than the terrestrial mantle by many times, by about 5 times. So it's about 50% iron end member, whereas the mantle is about 10% iron end member. If we go and then analyze all of the olivines on all of the meteorites that have ever been recovered from Mars, we again see the same thing. All olivines on Mars have much more iron than the terrestrial mantle. And the ones that are really important to focus on are these olivine-rich rocks, right? If we're going to serpentinize a rock, we're going to serpentinize the olivine-rich ones, these ones known as shergottites and dunnites. So if we want to understand this hydrogen greenhouse on early Mars, how you generate a hydrogen greenhouse, you can't look at Earth's mantle, right? You've got to look at different rocks that exist in Earth's mantle. You've got to look at something that has much more iron. Where can you find that? The Duluth complex of Minnesota, USA, which happens to be where I did my PhD as well. So through sheer luck, I ended up with some of these rocks early on in my grad school days. And through studying Mars, I realized that those rocks are actually the perfect analog for Mars and serpentinization on Mars. This is where that is. So there's Minnesota in this map of the US. We see this Duluth complex, and those yellow layers on the basal part of the Duluth complex are very rich in the mineral olivine. And that's shown on the right-hand side here. What you can see right away, and anyone that's ever seen a serpentinite will realize this, is these rocks are much browner or yellower than most serpentinites. And it's because of all of that iron that's in this serpentinite, that's in this olivine that's being altered to become serpentine. The other thing that you see right away is the formation of the mineral magnetite. That's the black stuff there. That black mineral contains oxidized iron as well. Okay, so going back to this plot again, remember left to right is the degree of serpentinization. Bottom to top is the generation of hydrogen. So this is for Earth. And then here I've grayed out those same points and plotted them for Mars, or plotted them for the Duluth complex. And what you see actually, and I hope that you can see this on the screen, is that, as my high school history teacher used to say, the more things change, the more they stay the same. We are generating the same fraction of oxidized iron as we increase the degree of serpentinization from left to right. But if we then calculate the amount of hydrogen we generate, or the amount of oxidized iron in total we generate, we see that that is a factor of 5 greater. So again, the process is the same. It's producing a slightly different mineralogy, but it's producing much, much more hydrogen, around 5 times much more hydrogen, which means that a rock on Mars that's only 20% serpentinized will produce the same amount of hydrogen as a rock on Earth that is 100% serpentinized. That's got profound implications for how much hydrogen you make on early Mars. So what's happening here, and I showed it in that thin section image, hydrogen is being produced as magnetite, that's that black mineral that we saw, and iron 3 bearing serpentine, a mineral known as hissengerite, which I personally hadn't heard of until about 4 or 5 years ago, and now is quite an interesting mineral for Mars. So this is a plot from Bethany Ellman from 12 years ago now of all of the potential identifications of serpentine on Mars. This is done using an orbiting spectrometer, satellite-based spectrometer around Mars. Every place they look that has a black dot means that they didn't find serpentine. The squares are serpentine is probable, so it's likely there. And then the stars are, we've definitely identified serpentine. And what you see is very discouraging for those of us that work on serpentinites. There's not that many stars, right? But even at this amount of stars, or this many identifications of serpentine, they still would have produced significant amounts of hydrogen. But this new work that we've done by identifying this mineral hissengerite, now what I've plotted here as a magnetic map, so this is enabling us to identify those magnetic anomalies that will be produced by the magnetite produced during serpentinization. The white circles are potential identifications of iron 3 bearing minerals like hissengerite. And what this tells us is that perhaps the stars aren't telling the whole story. Perhaps the planet actually has quite a bit more serpentine than previously thought. And in the process, there was probably a much easier way to make a hydrogen greenhouse than previously thought based on that prior study of spectroscopic identifications of serpentine. In the end, what's happening, serpentinization-driven hydrogen production would have warmed the planet. This is a potent greenhouse gas. It would have warmed the planet. But because Mars is significantly smaller, has a lower gravity, and has no magnetic field, all of that hydrogen just slips off into space. So essentially, the escape rate is proportional to the concentration in the atmosphere. If you have a lot of hydrogen being produced very quickly from serpentinization, you lose that hydrogen very rapidly to space. You cool the planet again, the liquid water stops being there, you can't run the reaction anymore. So you need to get the reaction started again in order to have that warm and wet history. And that's why those oscillations exist in that Wordsworth model. In-person lectures again. All right. So back to this slide. Habitability is a prerequisite for life. So I just showed you how you can make the solvent or stabilize the solvent water and the conditions, so the temperature being right to originate life. Now I want to talk more about the schnapps, and I think everyone wants to talk more about schnapps. Okay, so we have another Slido question here. Which of the vital schnapps elements is thought to be the hardest to come by? And there's a hint there at the bottom, the tooth. Carbon, hydrogen, nitrogen, oxygen, phosphorus, or sulfur is the hardest ingredient to find on planetary surfaces to originate life. Again, there's a hint of a tooth. Okay, everyone is pretty comfortable with carbon, hydrogen, and oxygen being there. Fair enough. Sulfur, perhaps. Phosphorus is winning. Shouldn't have given you the hint. All right, it is phosphorus. Thanks everyone for responding to that. And why do I give the hint of the tooth? It's because if phosphorus was super soluble and always available in natural waters, our teeth would be super soluble and available in our spit, right? And so we'd be just spitting our teeth out all the time. And we're not doing that, which means that phosphorus is insoluble. Okay. This is a picture of a place in British Columbia, Last Chance Lake. And so I do lots of fun outreach stuff with grade school children. And one of the children asked me about this picture, and they said, why is it snowing on the lake and not on the grass around the lake? That's not snow. That's actually sodium carbonate mineral. Imagine all of the muffins you can make with all of this sodium carbonate. So there is that lake. And so this is fall of last year. This is Last Chance Lake in British Columbia. It's almost completely dried out except for some very small pools of water. So what made that lake is evaporation, and what made it precipitate sodium carbonate instead of some other mineral like halite or something like that is behaves according to a system known as the chemical divides. So chemical divides are essentially a choose your own adventure for natural waters as they evaporate, but it's all preordained by the ratios of these elements that they have when they begin evaporating. So I'm going to show this plot here from a paper that Nick Tosca and I have coming out in Elements next year. Going down the page will be evaporation, and you'll see branches, right? So decision points in this choose your own adventure for the water as it evaporates. And you'll see if, for example, the water has more alkalinity or more bicarbonate than it has calcium, it'll go one way versus another, and so on. So here we go. First thing that happens when you evaporate in natural water is you precipitate calcite. Then it has a choice. Is it going to go and precipitate gypsum, magnesium, calcite, dolomite, or magnesite? Or then is it going to make our favorite last chance lake, sodium carbonate there? If you go down further, which we'll talk about later, you precipitate gypsum and you might become a magnesium sulfate lake, sort of at the very end of the chemical divide pathway. But right now we're going to focus on this guy, the sodium carbonate rich lakes. And so what the big requirement for that is that the alkalinity in the initial solution, so the groundwater that feeds into the lake, must be greater than 2 times the concentration of the calcium and magnesium in the lake or in the groundwater. And so this is an example of that beautiful sodium carbonate mineral there. This is a plot of a paper from Toner and Catling in 2020. What they showed, and it was really quite intuitive once they showed it, is that as you evaporate these waters, you increase the inorganic carbon that's simply remaining in equilibrium with the atmosphere, you're increasing alkalinity. You dump out all of the calcite, right? So you have all of this inorganic carbon that is orders of magnitude greater than the calcium in the initial solution. So the calcium essentially goes to 0, and the phosphorus goes through the roof. So that's going from left to right here. Inorganic carbon for alkalinity increasing, phosphorus increasing in lockstep. These points up here are from Last Chance Lake in British Columbia. It has the highest phosphate content of any natural water that we've seen. And it's easy to believe that if the partial pressure of CO2 in the atmosphere on the early Earth was much higher, then the amount of phosphorus in early Earth waters also would have been much higher. So British Columbia, the best place on Earth to originate life, perhaps, right? All right, so this wet-dry cycling that happens here is vital to make nucleotides, to make the fundamental building blocks of life. This is just a nice schematic diagram of how that looks. So you hydrate these organic molecules, you make these initial biomolecules or cells here in the top. You evaporate it down to full dryness, you dehydrate that, and then you run the cycle again. You do that a bunch of times. That's one of the scenarios for how you make Darwin's warm little pond, how you originate life in Darwin's warm little pond. So, but the problem is, if you do evolve in a lake, and then it dries out, what's a poor little organism to do, right? How is it going to survive in this context if it's totally dry and it requires life to live? So what I've been doing is working with this fantastic group of geophysicists from here in our department. Rachel Lauer on the right-hand side here is another professor in our department. She says this picture looks like we just buried a body. We did not. But what we did do is image the subsurface with geophysical geochemistry, or geophysical chemistry, or geophysicstry, whatever, transdisciplinary academy, that's us doing it out there. And what we can do is image the subsurface using geophysical techniques to see this place in the lake where it has totally dried out. What does the subsurface look like there? Are there refugia or places where an organism could live even though the lake is totally dry? And so this is seismic refraction. So this is velocity. Again, we're just able to see how the waves are transmitted through the subsurface in this case. And what we see is that there is this place where the subsurface, or this water table place where the subsurface could live, or in the subsurface where organisms could live. So these nascent organisms, if they were to infiltrate with these very dense brines, would be able to follow or fall down into the subsurface and exist there until they encounter some impermeable rock, such as this intact basalt. And so Last Chance Lake sits right there on top of that basalt. We can use other techniques like electrical resistivity tomography, which allows us to image the conductivity of solutions in the subsurface. So this is essentially a proxy for the concentration of the various elements in the subsurface. So it's allowing us to get at where are those dense conductive brines in the subsurface, shown here in yellow, and where are there packets of groundwater. And you see there's very nice interfaces, lenses in the subsurface where they must be mixing. So again, if an organism can no longer survive in this very densely salty water because the water activity is too low, there is hope. They may be able to interact with this groundwater, fresher groundwater that's infiltrating in the subsurface. And to put any concerns at ease, this is great work done by a master's student we had here, Shane Bossire, a number of years ago. Biology seems to have no role in affecting the phosphate concentrations of Last Chance Lake. So folks often say whenever I give talks like this, that, oh, that phosphate was all just bird poop or cow poop. And there's a lot of cow poop out there, but that phosphate is not coming from cow poop, it's coming from evaporates. And that is shown here by this chlorine concentration linear plot with phosphate concentration. Okay, so I talked a bit about the ingredients, and I talked about the solvent, I talked about the conditions, and I want to talk about when conditions might potentially go bad. And for example, what happened on Mars when it transitioned to be the cold, wet place that it is today. So Curiosity rover has been on Mars for 10 years now, a decade. It landed there in 2012. In August, it celebrated a decade on the surface of the planet. And this pathway here, so it landed down here in Bradbury Landing, and has slowly been making its way up this mountain in the center of the crater, known as Mount Sharp or Aeolus Mons. And as it has gone up, it's getting closer and closer to what I think is one of the most important units on all of Mars, this magnesium sulfate-bearing unit. Why is that important? And how do we know that we're coming up to it? So this is Curiosity traveling over the surface of Mars in an animation, and you'll see something very cool. It has a laser on it that allows it to shoot rocks surrounding it up to several meters away and get the chemistry of those rocks. And so what has been coming out of this data as it's been lasering these rocks is we're seeing more and more of these sulfate-bearing minerals as we approach this magnesium sulfate-bearing unit. And that's shown here. So this is a nice paper by William Rapin showing, again, we start down here in the average bedrocks, things that we look like where we were at in Bradbury Landing. But as we've risen up and driven further and further up into onto the strata of Mount Sharp, we've seen more and more calcium sulfate-bearing minerals. And eventually, where we are going now, we're going to start seeing magnesium sulfate-bearing minerals. So how salty is the ocean? To precipitate salty minerals like gypsum or magnesium sulfates, obviously waters must be very salty, but I want to be able to compare against something like the ocean as I go forward here. So please answer this. So what I'm talking about here is how much of the ocean is actually water versus how much of it is something else, salt. So the ocean is probably the saltiest solution a lot of us will ever come in contact with in our life, unless we are in Alberta here. People work on reservoir brines here as well. So we have three options: 3.5% salt, much less than 1% salt, or 35% salt. So one end of the spectrum, nearly half of the solution is salt. At the other end of the spectrum, basically none of it is salt. So the answer is the one that everyone is getting, which is great, 3.5% salt. The ocean is about 3.5% sodium chloride and other ions in solution. So what that means is this profound agent of change on our planet is mostly not stuff, right? It's mostly just water that's moving that stuff around. I've always found that to be quite interesting. To precipitate a magnesium sulfate brine, we've got to be about 5 times saltier than that. So then we're really talking about getting closer to that tens of % of salt. And those brines end up being a lot denser also than the salt in the ocean, or than the ocean waters. Okay. So this happened in Mars's ancient past about 3.5 billion years ago. We went from having big river valley networks that precipitate lots of clay minerals to a point around 3.5 billion years ago where we make sulfates and evaporates. And that is the place where Curiosity is approaching right now. And this is a press release from just a little over a week ago. Curiosity Mars rover reaches this long-awaited salty region. It drilled its first drill sample into the Kanaima sample target not too long ago and proved that there is magnesium sulfate minerals, one of which is the mineral epsomite. So to get there, again, we can go down our chemical divides, make our calcite, make our dolomite or magnesite, and then eventually you precipitate the calcium sulfate mineral gypsum, which many of us are familiar with, and then you make a lake that is extremely concentrated because you've now gone through thousands of times of evaporation to get down to this magnesium sulfate-rich brine, of which the best example in the world is Bass Lake in British Columbia. Another lake very close to the greatest place on Earth to originate life, Last Chance Lake. So here is the model for what we believe is happening at this interval in Gale Crater. We precipitate calcium sulfate. This calcium concentration here increases until it hits gypsum solubility, and then that drops off. And then what happens is we continue to evaporate and we make magnesium sulfate minerals like epsomite. Epsomite is exactly what you think it is, the Epsom salt that you put in your bath. Everyone recognizes that Epsom salt is extraordinarily soluble, right? You could just toss that in the bath, it will all dissolve because you need to be extremely evaporative in order to make that. And so this is a model for what we think is happening there at Gale Crater. Turns out Bass Lake looks just like that conceptual model. So we have a groundwater recharge entering into the lake, making this beautiful yellow lake down here. And we end up with this issue, right? So evaporative conditions are required to originate life. I talked about that earlier on in the second part when we talked about needing to make nucleotides by wet-dry cycling. But it's possible, if not likely, that magnesium sulfate brines become so concentrated that the activity of water drops to near zero, and therefore things can't live. Think about soy sauce. Soy sauce is very salty. None of us ever really do anything to keep microorganisms and mold and things like that out of there because it's too salty for organisms to live. It is possible that magnesium sulfate lakes become too salty for organisms to live. So this is where I'm at as part of the Curiosity rover team and mission. How wonderful that we've met with the paradox, right? It's extremely salty. It's required to dry out the lake entirely to make nucleotides, but it might be too salty to originate life. Now we have some hope of making progress. So thank you all very much. I want to point out that I'm not the only person that did the research. You saw Rachel Lauer's team, folks from Mark Strauss's group here at the University of Calgary and Bernard Meyer's Applied Geochemistry group have also done work. And I want to thank NSERC and the Canadian Space Agency for funding this research. And I'm happy to answer your questions. I'm gonna bug it off.
All right. We're multitasking here. Thanks, Ben, for sharing that fascinating research with everyone this evening. It's a great start to our series this year. I know already from the questions that I'm getting online, the Gallaghers are certainly interested in this one. I know many of you, as I mentioned at the start, will have questions for Ben. We're going to take questions with the online crew first. And so for those of you online taking this in, enter your questions in the Q&A box, please, at the bottom of your Zoom. I will juggle this laptop and work with Ben here to ensure that he hears all of them and engages you all with his answers there. we do appreciate all the questions we get. We'll get through as many as we possibly can. With that, then I'm going to bring you over here to the hot seat. And our first question is from Fred Gallagher. Liquid water is consumed on Mars to make hydrogen. The hydrogen leaks away and the planet cools. Does this mean that life cannot occur because the liquid water is consumed before it can help to create life?
That's a great question. And I think there's a couple of ways to think about that. One is, yes, you're making hydrogen. That hydrogen is H that escapes to space. And we see that in the isotopic signals of the water that's still there. There's clearly hydrogen that's zooming off into space over the geologic history of Mars. But at the same time, there was enough water there to make hydrogen, and not all of that hydrogen, or not all of that water was made into hydrogen, right? So I think it's a little bit of, we need the water to make the hydrogen, but you're not getting rid of all of it to make that hydrogen. I mean, at the same time, you're locking up some of that water in the serpentine minerals, which then still exist on the planet today. So there is still lots of water there. If we go and do an inventory of all the clay minerals on Mars, there's still lots of water on the planet, even though a lot of it has escaped as hydrogen to space.
Excellent. A follow-up question that I'm sure a few people had a question about here. You showed a plot, the map of no serpentine, probably serpentine, and definite serpentine. And so how do they make positive identification of minerals on that scale?
It's truly an extraordinary feat of science and engineering that has come from the CRISM spectrometer on Mars. So compact reconnaissance something spectrometer for Mars is what CRISM stands for. And what CRISM is doing is using light that's reflected off the planet to then look at a spectrum that is coming from that light. And by examining the features of that spectrum, you can actually get at the mineralogy of the sample that produced that spectrum. It's not perfect, but it is extraordinary that we can make maps of the entire surface of the planet using such technologies. Yeah.
Rob Kendall asks, what was the source for the refraction survey that you guys did?
Sledgehammer. That's true.
We can all envision that. Yeah. Okay. Peter Bukowski asks, do you have dissolved silica concentrations in these lakes and waters?
Yeah, we've measured the dissolved silica, and actually this is something I didn't really talk about today. The silica concentrations are really quite low. The reasons they're quite low are a bit mysterious. I believe it has something to do with the precipitation of phyllosilicate clay minerals early on in the evaporation of the waters. But then what happens is, as that water with very little silica infiltrates into the surface of Mars, for example, we see what is Tom Bristow has declared as clay mineral destruction. So you have these magnesium sulfate-rich brines, very little silica, infiltrating into the subsurface, dissolving all of those clays that used to be there. And there's a unit that should be continuous on Mars, but is not, because it's believed that magnesium sulfate-bearing brines infiltrated into that part of Gale Crater.
Question from Tom Gallagher. What is the origin and cycle that creates lithium salts?
I think I saw Ian Hutchin. I don't know. I can answer that. Yeah, it goes into the clays. That's right. But it's not lithium chloride salt, which I think is what he's asking. Yeah.
I don't know if there's,
so the lithium goes into clays, right? That's definitely happening. But I think he's asking about how we make a lithium deposit, which I don't. Yeah.
This is kind of a fun game here. Yeah, stump the professor. I like that. Excellent question. Clint Tippett, why would Martian and terrestrial olivines be of such different composition?
That's a wonderful question. I'm super excited that you asked that question. It has to do almost entirely with the redox state of the planet when it's accreting. So on Mars, well, I guess I'll give the terrestrial example that we all know better. We have an iron core, right? Because our planet was considerably more reducing when it was accreting, a lot of our iron went into the core. On Mars, it was more oxidizing when it was accreting, and a lot of that iron went into minerals like olivine instead of going into the core. That's exactly why that happened.
Excellent. All right. Alexander Briggs says, how does hydrogen work then as a greenhouse gas? And it's a little.
Yeah, this is Robin Wordsworth or Edwin Kite would be great people to ask about that. But essentially, what happens is you have hydrogen go up into the atmosphere, and it competes or it communicates with things like CO2 in the atmosphere to then block heat that's leaving as it's reflected off the planet, similar to the way CO2 does, but in a slightly different way. Yeah.
I guess this kind of dovetails onto that. So I'm not sure this adds much here, although Fred Gallagher had asked, I think in line with that, what happens to the hydrogen that is created on Earth when surface occurs? Does it get trapped anywhere?
Oh, yeah. So, for example, our good colleague at the University of Toronto, Barbara Sherwood-Waller, has studied these massive accumulations of hydrogen that occur in places like Timmins, Ontario, in these very deep mines where there's been potentially radiolytic production and or serpentization happening in rocks for billions of years. And you have a big, massive gas deposit of hydrogen there on the subsurface.
All right, this will be our just about our time. Keep things moving forward here. This will be our last online question. As I said, we will get a chance for those in the audience to do to query Ben here in a moment. How much water per volume is stored in serpentine?
Volume, I can tell you weight percent, and weight percent for serpentine, the terrestrial serpentines like lizardite is about 13%. But for minerals like, and I can show this plot again. Along the top here, you'll see I've annotated minerals. Lizardite here, about 13%. Kissingerite and greenolite, the iron-rich serpentines, have about 7.5 to 9%. And that's because iron is much heavier than magnesium, right? If you increase the amount of weight that's being contributed to your cations, the silica decreases accordingly. So between about 9 and 13%.
So for those of you online, thank you so much for tuning in tonight and for your engagement through this lecture. I hope this presentation by Dr. Tutolo provided an opportunity to learn more about his research and kind of things going on here in the Department of Geoscience. Thanks, Ben, for really an engaging and exciting talk. Obviously, we all want to hear what happens now with this latest samples collected on Mars, and I'm sure you'll be around to tell us about that soon. Just a reminder to all of you out there that our next Gallagher Colloquium series presentation is on Thursday, November 17th. And it's going to feature U Calgary alum, Dr. Bethany Ladd. And she'll be here to discuss, can mine tailings become massive carbon sinks? You can register online for that, whether you're join us again online or want to come here and be with us in person. Again, thank you for joining us and enjoy the rest of your evening.